Welcome to the third of a series, Demystifying Pointers in C. I'd like to start by thanking everyone who spent their time to correct the flaws in my previous ones. So this is mostly going to be me addressing those errors and building on top of them. First, this is called the address of operator, not the reference operator. Second, this was supposed to be 99. Third, I got the memory alignment wrong. To be brief, it's a method that governs how data is stored on a computer memory. It says that the starting byte of a data type has to be a multiple of its size. Consider num, it's an int whose size is 4 bytes and hex98 in decimals is 152, which in fact is a multiple of 4. So we can say that that's aligned. But the problem is with the pointer. I said that on my system the pointers are 8 bytes long. So according to the alignment practices, the starting byte of the pointer should be at an address that's a multiple of 8. But here, it's A5, 165 in decimals, obviously not divisible by 8. So the correct representation would be here at A0, or possibly starting at any other address that's a multiple of 8. Fourth, I said that the size of a pointer depends on the operating system. The correct statement would be to say that it depends on the architecture of the compiler. I'm interested in the following two, the 32-bit one and the 64-bit one. This determines the number of bits that can be used to represent an address. As a side note, a 32-bit application can also use the x86 notation that comes from the 32-bit Intel processors family 8086 and x64 because 64-bit. A 32-bit machine can handle addresses ranging from 32 zeros through 32 ones, and 32 bits equals 4 bytes. So when dealing with addresses that can be 32 bits long, we'll need pointers of size 4 bytes. And the 64-bit ones can handle addresses as long as 64 bits, so the pointer size needed would be 8 bytes. The size of a pointer is directly determined by the compiler, a program that converts your source code into an executable. We can have 32-bit and 64-bit compiler programs. A compiler is installed on top of an operating system. An OS can be of a 32 or a 64-bit type, and the operating system is installed on a hardware, which again can be of a 32 or a 64-bit architecture. We can have many combinations here. Install a 32-bit OS on a 64-bit architecture, a 64-bit compiler on a 64-bit OS, a 32-bit compiler on a 64-bit OS, but there cannot be a 64-bit program on top of a 32-bit program or architecture. The point is, the size is going to be directly determined by the compiler. If it's a 16-bit program, it'll assume address is 16 bits long. So the pointers will be 2 bytes. If it's a 32-bit one, 4-byte pointers, and for a 64-bit one, 8-byte pointers. This is the actual address of a variable on my 64-bit machine. It's 12 hex digits long, and each hex digit will be able to represent all the numbers formed by 4 bits. So times 4 equals 48 bits. But why not use 16 hex digits to use all 64 bits? I will not get into explaining that in this one, but I'd just like to show the space of all addresses we can have with 48 bits. Well, how many different values or addresses can be represented with 48 bits? 8 bits, that is, a byte, can represent 2 to the 8, that's 256 different values. So 48 of them will be able to represent 2 to the 48 values. We can expand that to this. The number of values we get here would mean we'd be able to address those many bytes. So how many bytes are these? 2 to the 10 is 1 kilobyte. 2 to the 20 is a megabyte. 2 to the 30 is a gigabyte. 2 to the 40 is a terabyte. And we have 1 terabyte times 256, that is 256 terabytes, which means we can represent 256 TB of memory with the 48 bits of 64. We're currently not in an age to use a memory bigger than that, so 48 bits would do just fine. But in case we do get there, the current size of a pointer, 8 bytes, will still be able to hold addresses as long as 64 bits. That's it for this one. Catch you in the next one. Thanks for watching.